Patty's Calculus videos, written and performed by me, Patty Leitner.
Part 4. Integrals. Section 5.3. The fundamental theorem of calculus and the definite integral.
Lesson 1. The fundamental theorem and definite integrals. Part 1. In this section, we're going to talk about two main ideas. One is what's called the fundamental theorem of calculus. So you can imagine if it's called the fundamental theorem of calculus, it's pretty important, and it is. And the other is the definite integral. So those are our two topics for this section. Well, you might remember that at the end of the last video, I said that in this section, we are going to see a connection between the antiderivative idea that we had back in section 4.9 and the idea of areas underneath a curve that we were talking about in section 5.1. And those ideas are brought together by this theorem that I mentioned called the fundamental theorem of calculus. So we'll talk about that theorem in just a few minutes. Before we dive into that theorem, however, I want to pose a problem that we didn't talk about in 5.1. We had this example back in 5.1 where we looked at the curve y equals square root of x, and we considered how to approximate the area under that curve on the interval from x equals 0 to x equals 8. And remember, we did that using these right-hand rectangles. That's what I've shown here are 8 approximating right-hand rectangles. We did it with left-hand rectangles, and we even increased the number of rectangles to 16, to 32, and I think we went up to 1,024 rectangles. And the more rectangles we used, we saw that we got closer and closer to the exact area underneath this curve. But what if I pose the problem this way, and somebody gives you this example and says, find the exact area under this curve from 0 to 8. This is different from what we were doing before because we were finding an approximation for the area underneath this curve. And we found some pretty good approximations. You might remember, I'm just grabbing some of the overheads that we used in that last video. You might remember here was the work that we did for r sub 8. We broke it up into 8 right-hand rectangles. We figured out what the areas of each of these approximating rectangles was, and we got 16.3 something as an approximation for the true area under the curve, although we could see that this approximation was too big. And we even went to higher numbers of right-hand rectangles. Here's another overhead from what we did back in that section. Here we did r sub 16, so we broke it up into 16 rectangles, used the right-hand side to create the height of each rectangle, and we got a better approximation of 15.722. But again, we saw that it was a little bit too large. We did r sub 32, got an even better approximation, and we did r sub 1024. Well, we didn't actually do it, but my TI calculator did it for us, and we got an even better approximation. And I told you back then that the true area was 15.0849 something. How did I know what that true area was? That's really what's being asked for here. They are asking us to find the exact area underneath this curve. Wow, okay, so how the heck am I going to do that? Well, remember we said that the exact area would be what we get if we found the limit as n goes all the way to infinity. So instead of 8 rectangles, I basically chop it up into an infinite number of rectangles. It's the limit as n goes to infinity of our n approximating rectangles. So here what I did, although it shows 8 rectangles in my picture, you notice I'm starting out at my a value, which is also called x0. The next subinterval is at x1, x2, x3, and my last subinterval I'm going to call xn. So I'm really going to think of this not as 8 rectangles as the picture shows, but let's think of it as n approximating rectangles. Well, we said the exact area is the limit of the areas of those n approximating rectangles. Let's write down what that is. And we did this in the last video. We said, well, it's the height of the first rectangle where we evaluated at the right-hand endpoint. So that was f of x1 delta x plus the second rectangle. Its height is f of x2 delta x plus the third rectangle's area, f of x3 delta x, and so on. We just put dots in here because we don't know how big n is. And we go all the way up to f of x sub n times delta x. And the exact area would be what we would get if we figured out what this was and then allowed n to go to infinity. Well, I know what f of x is. F of x is square root of x. So I can actually figure out what f of x1 is for this particular example. That would just be square root of x1. And I multiply by the width of my subinterval, delta x. In the same way, the next term, f of x2, would be square root of x2 times delta x. And then I would have square root of x3 times delta x. I'll put my plus dot 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 for the missing terms, and my last term, would be square root of xn times delta x. Well, that doesn't really look any easier to find the limit of that as n goes to infinity than our original. It turns out that this x1, x2, x3, and so on, and also the delta x, can actually be expressed purely in terms of n. Well, how would I do that? Let's think first of all about the delta x that's right here. Remember that delta x is found by doing my whole interval, b minus a, the width of that whole interval, and dividing by the number of rectangles that I have. So for this example, my b is 8, my a is 0. So I'd have 8 minus 0 over n. So it looks like delta x would be 8 over n. Okay, so all of these delta x's that are in here could be written as 8 over n. This is 8 over n. I'll put a little time sign because we're going to multiply it by the square root of something. And here's a little 8 over n. And at the end, I have a width of 8 over n. So I've written at least my delta x purely in terms of n. Well, what about this part, the x1, the x2? I can actually figure out what those are in terms of n as well. Remember, we said that our delta x is equal to 8 over n. So that means the width of this interval, and in fact of all the intervals, is supposed to be a width of 8 over n. Well, if I start out here at x equals 0, what would x1 have to be if I'm moving 8 over n units to the right? X1 would have to be equal to 8 over n. And to figure out what x2 is, I'd be moving another 8 over n units to the right, 8 over n. So x2 would have to be 8 over n plus another 8 over n. That would be 16 over n. So x2 is actually 16 over n. And by the same token, if I move another 8 over n units to the right, another delta x units to the right, I would have x3 would be 8 over n plus 8 over n plus 8 over n. That would be 24 over n, and so on. And it turns out that you can rewrite each of these in a little bit more convenient form. I'm going to rewrite the x1 as 1 times 8 divided by n. And I'm going to rewrite the x2 that I have here at 16 over n. That could be written as 2 times 8 over n. And the x3 was 24 over n, could be written instead as 3 times 8 over n. So there's a pattern here to what the xi's can be described as, and the very last one that's over here at the end, well, for the first one it was 1 times 8 over n, the second one was 2 times 8 over n, and so on. So the nth one would be n times 8 over n. Okay, let's go ahead and try to put that in. Notice what I have here then is a bunch of square roots. I'm going to try to write in what those are the square root of, but purely in terms of n. Let's see if I can squish it all in here. So I already wrote my delta x's here. So that delta x factor was 8 over n in each of these terms. But now I want to write what my x1 is in terms of n, and we said right up here that x1 was 1 times 8 over n. I'm going to leave it in that kind of funny unsimplified form, 1 times 8 divided by n. And our x2 was 2 times 8 over n, 2 times 8 over n. And our x3 was 3 times 8 over n. And our xn was n times 8 over n. Okay. Well, I'm just going to simplify a little bit more, and I know this is some kind of messy algebra. Don't worry too much about the details here. The conclusion is what we really want to look at. But just notice that all of these square roots have a common factor of 8 over n inside them. So I'm going to pull that common factor out, and there's also a common factor of 8 over n in each of these terms, the delta x that we had on the outside. So it turns out that we can write this factor as, let's see, how am I going to do it? Square root of 8 is 2 root 2 times 8 is actually 16 root 2. Don't worry too much about that calculation. And down below I have a root n, because this is underneath the square root, times an n that's outside the square root. That would actually be an n to the 3/2 power. It's n times root n. And I still have a square root of 1 that I'm going to leave there. So I'm going to put square root, and I'll write the 1 in red just so that we can identify it with this 1 that's up here. The next term has exactly the same factor out in front, but it will have a square root of 2 instead of a square root of 1. So I again get 16 root 2 over n to the 3/2, and it'll be times the square root of 2. And the next term has exactly the same factor of 16 root 2 over n to the 3/2 in it, but it will be times a square root of 3, and so on, up to the very last one, which again has a 16 root 2 over n to the 3/2 factor in it, and what's left over in the last term is a square root of n. So you can check yourself by simply multiplying this out, that this term and this term are identical, and this term and this term are identical, if you didn't exactly follow my multiplication and simplification there. Notice that all of these terms have this common factor of 16 root 2 over n to the 3/2. So I'm going to pull that out. 16 root 2 over n to the 3/2. And what would I have left if I pull that out? Well, I'd have these things that are in red. The square root of 1 plus the square root of 2 plus the square root of 3 plus, and so on, up to the square root of n. Well, this looks a little nicer than what I originally had up here when I was saying, how am I going to find the limit as n goes to infinity of this thing? Now I'm asking, how do I find the limit as n goes to infinity of, and at least I have an expression that's written purely in terms of n. I don't want you to worry too much about these details in here. The main thing I want you to think about is, even if I rewrite all of these xi's purely in terms of n this way, I'm still asking you to do something very difficult. I'm asking you to find the limit as n goes to infinity of this crazy looking expression. This factor out in front doesn't look too crazy, but this one's really crazy. It's got some dots. It's not even what we call closed form. It's got terms that are missing. So the question is, how do I find this limit? As n goes to infinity, it's not at all clear to me how to find that limit. And the answer is that for most functions, it's difficult, extremely difficult, or impossible to actually find that limit of this sum using kind of the traditional methods that we've talked about. For many functions, it would be impossible to find this limit by simply trying to somehow rewrite this in closed form and then figure out what the limit is as n gets larger and larger and larger. So I'm going to say difficult or impossible to do. We really can't do it the way we normally do things. So the question becomes, how am I ever going to find the exact area under this curve? I can't seem to figure out what the limit as n goes to infinity of my right hand approximating rectangles r sub n is. I just don't have a way of figuring out that limit. It looks impossible to me. Well, luckily, there is a wonderful theorem that gets us out of our dilemma of trying to find that difficult limit. And I called it a magical theorem that helps us out. And the name of that theorem is the fundamental theorem of calculus. And you can see that it's an important theorem in the study of calculus just by the name, fundamental theorem. Well, what does the fundamental theorem say? It has some conditions on f. It's really the same conditions that we had back when we were looking at areas under curves in section 5.1. It says if f is continuous and f of x is greater than or equal to 0 on the interval from a to b. So what does that mean in terms of the graph? Here's the black graph of y equals f of x. And what we're saying is that it's continuous, it's unbroken between a and b. Actually, it turns out that you can have a finite number of piecewise discontinuities, but for now we're going to assume that it's a nice continuous curve. And f of x greater than or equal to 0, remember that means that the black curve is always above or at worst on the x-axis. It might touch the x-axis, but it does not go below the x-axis on the interval from a to b. So if you have those conditions on your function f, then the exact area underneath the curve from A to B, so this green area that I have under the black curve from A up to B, that exact area is given by the following very simple formula. The area is capital F of B minus capital F of A, where capital F of x is any antiderivative of little f of x. So to find the area under this curve, little f of x, all I do is find an antiderivative of little f, that's what they're calling capital F, and I evaluate that antiderivative at the right-hand endpoint, where I want my area to stop, and subtract the value of that antiderivative evaluated at the left-hand endpoint, where I want my area to begin. Super, super simple. And you can now see in this theorem the connection between the antiderivatives that we talked about in section 4.9 and the areas under curves that we talked about in 5.1. So this theorem connects those two ideas that may have seemed very different from each other before. To find the area under a curve, basically all I do is find its antiderivative. I evaluate it at the right-hand endpoint, subtract the value at the left-hand endpoint, and voila, I have the area under the curve. Well, let's see how we could apply that to that example that we worked so hard at in 5.1, where we were trying to use rectangles to estimate the area under this curve, y equals root x, from 0 to 8. So we were trying to get an estimate for the area that's shaded in green here. Now we can find the exact area, and we can do it in a very short amount of time. So let's see how we do it. I put down step 1. Well, I see from my fundamental theorem that I need an antiderivative of my function, and this is my function little f of x. That's root x. So I need an antiderivative of f of x equal root x. So that's my first step. Let's go ahead and find an antiderivative, and I'm going to call that antiderivative capital F of x. It's just traditional to use a capital F for the antiderivative. So I say, oh, I need an antiderivative. Well, that just means I want to integrate my function little f of x. Okay, well, what is little f of x? In our case, it's square root of x. And do I know how to find the set of antiderivatives of square root of x? Sure, as long as I write it as a power of x. Then I can use my power rule for indefinite integrals. So I'm integrating x to the 1/2. You've got to go back and remember how to integrate. Remember, you're thinking backwards or using the power rule for integrals rather than the power rule for derivatives. So remember that you want to add 1 to this exponent. So I'm doing 1/2 plus 1. That gives me a new exponent of 3/2. So I'm going to get x to the 3/2. And then we need the reciprocal of that new exponent out in front. It's 1 over 3/2. Invert and multiply, you get 2/3. And of course we could add on any c to that. So the set of all antiderivatives would look like this: 2/3 x to the 3/2 plus c. Well, I noticed that up here in the fundamental theorem it says that capital F of x can be any antiderivative. In other words, it can be any one antiderivative. It doesn't have to be the set of all antiderivatives. And remember, when we write this plus c, c can range over all real numbers, so we're really talking about an infinite set of antiderivatives here. I only need one antiderivative, and so we usually choose c equal to 0. I'll put up here, only need an antiderivative. It can be any one of the infinite number of antiderivatives, and the fundamental theorem says I only need one antiderivative. So I'm going to choose the easiest one with c equal to 0. So I'm going to choose f of x, capital F of x, to be the antiderivative 2/3 x to the 3/2, and you can think of it as plus 0. So I've just replaced the c with a 0. Okay, I've got my antiderivative. So that is the end of step 1. Let's go to the next page and do step 2. So I'm going to write the antiderivative that I chose here, since we're doing step 2 on a separate page. We just decided that capital F of x was 2/3 x to the 3/2. So that's the antiderivative that we chose from the last page. Let me move that aside. What the fundamental theorem says then is that for the exact area, all I do is take my antiderivative, evaluate it at b, and subtract the value at a. Now let's remember what those b's and a's were. In the fundamental theorem, if I go back to the last page, b was the right-hand endpoint where I wanted my area under my curve to stop, and a was the left-hand endpoint where I wanted my area to begin. So we do f of the right-hand endpoint minus f evaluated at the left-hand endpoint. Well, what are my a and b in this example? My a and b are 0 and 8. So 0 is going to be my a value in the fundamental theorem, and 8 is going to be my b value. Okay, let's go back to this page. Maybe I'll just move that to the left so we can refer to it. So for me, I'm supposed to do the antiderivative evaluated at the right-hand endpoint, 8, minus the antiderivative evaluated at the left-hand endpoint, 0. Well, here's my function, so let me go ahead and plug that in. I'm going to be figuring out 2/3 times 8 to the 3/2 minus 2/3 times 0 raised to the 3/2. So that would be the antiderivative I chose with c equal to 0. I evaluated it at the right-hand endpoint and then subtract the value at the left-hand endpoint. If it's hard for you to see what that's equal to when it's written as a fractional exponent, remember that you could rewrite this in root form. 8 to the 3/2 is the same thing as the square root of 8 raised to the 3rd power. And the same thing here with the 0, although you can probably guess what that will come out to be. It's the square root of 0 cubed. So just writing it in the root notation makes it easier to calculate. Okay, so square root of 8 raised to the 3rd power, that would actually be, let me simplify it just a little bit more. It's root 8 times root 8 times root 8. So you could simplify this and write it as 2 root 2. That's the same thing as square root of 8 cubed. And here I can see that square root of 0 is going to be 0, and I raise it to the 3rd power, that's going to give me 0. So that term just drops out in this case. And if I go ahead and calculate that, well, that would be 2 cubed times root 2 cubed. Root 2 cubed is 2 times root 2. So I believe you can go ahead and simplify that yourself. I believe we will end up with 32 root 2, because it's 8 times another 2 times this 2 gives me 32. I have 1 root 2 left over, all divided by 3. And this number is the exact area that we were looking for. It comes out to be approximately, I just put it into a calculator, 15.0849467. And this is the number, you might remember back in section 5.1, I told you I knew magically what the true answer was, that it was 32 root 2 divided by 3, or approximately this number, and we used that number to compare to all of our different estimates, using different number of rectangles to estimate this area underneath our curve y equal root x. But now, very simply and very quickly, in just a few lines, I found not an approximation, but the exact area underneath the curve. So that is the exact area, this exact green area is 32 root 2 divided by 3. And that's pretty cool. So this fundamental theorem, that's why I call it magical. It's just amazing. We found the exact area under this weird shape, not a triangle, not a rectangle, not a circle, nothing that you ever knew how to find the area of before, and you've just found the exact area of this weird looking shape. And another comment that I wanted to make is just that because this number that we end up with, 15.08 whatever, is very close to the estimates we had back in 5.1. I'm going to show you that page that we looked at just a few minutes ago from 5.1, and here were some of the values that we got. I think when we got down to the average of the right-hand rule with 1,024 rectangles and the left-hand rule with 1,024 rectangles, we averaged those. We got this number, 15.0848 something. And I said that the true area was this number that we got right here, 15.0849447. And because this value that we just got using the fundamental theorem is so close to what we get when we do a really good estimate with a lot of rectangles, it gives us some confidence that this fundamental theorem is probably true, because I just pulled this example out of a hat. That is certainly not a proof of the fundamental theorem, but it gives us some confidence in it, and we will prove it. We'll do at least a kind of picture, intuitive proof of it very shortly. Now, before we go on to this question that's in the middle of the page here, what if I'd chosen a different antiderivative for little f of x? We'll answer that question in a moment. I just want to remind you as well that not only have we found the exact area really in a very easy way, but I want to remind you that this exact area that we found was the answer to that really tricky limit that we had earlier. So remember that at the bottom of the first page of this section, we said, well, if we wanted the exact area, we had to do the limit as n went to infinity of the f of x i's times the delta x is the sum of those, the sum of the rn's. And we went all the way down. We did a bunch of algebraic manipulation and cutting all this stuff up and writing all of the x1 and x2's in terms of n. It was a lot of work just to get to this, but then we were left with this really difficult or perhaps impossible limit to try to find. The limit as n goes to infinity of 16 root 2 over n to the 3/2 times this sum that has n terms in it. It has a dot, dot, dot. We had no idea how the heck we were going to figure out that limit. Well, that limit is equal to the exact area underneath our curve root x, and we just found that exact area. We just found that area is equal to 32 root 2 over 3. So that's actually the value of this crazy limit that we were trying to do. So we just found out that 32 root 2 divided by 3 is what this limit ends up being equal to. We knew we had a continuous function, so that limit definitely exists, and it's equal to 32 root 2 over 3, but we had no way to do it in a sort of traditional sense of finding limits, but now we have a brand new way to find the limit of something crazy like that. So that's just a side note that I wanted to remind you. We actually found this limit, but in a totally different way by applying the fundamental theorem of calculus and getting this answer of 32 root 2 over 3 as the exact area under our curve. Okay. Well, one thing that you might be thinking about is the following. What if I'd chosen a different antiderivative? Remember I said we were going to choose the antiderivative with c equal to 0? If we just go back to the last page again for a moment, we chose c equal to 0, and I said let's choose this antiderivative, and the fundamental theorem said it can be any antiderivative, any one antiderivative of little f of x. So what if I chose a different c value? What if I chose instead something like c equals, I don't know, 5? Something like that. So that now the antiderivative I'm choosing, capital F of x, is 2/3 x to the 3/2 plus 5. Let's see what happens, and I'll show you that it doesn't really matter. You'll get exactly the same value for the area under the curve if you choose a different antiderivative. So now I'm going to choose 2/3 x to the 3/2, but instead of adding 0 onto that, I'm going to add 5 onto that, and I'll just put the plus 5 in red. Well, according to the fundamental theorem, I should still be able to do f of 8 minus f of 0 for this new antiderivative and get exactly the same answer. Well, how does that happen? Let's see. So the exact area is supposed to be f of 8, that's f of my b value, minus f of 0, that's f of my a value. And let's go ahead and plug in. For this function, for this antiderivative, capital F of 8 would be 2/3. I plug in the 8, raise it to the 3/2, but I have a plus 5 on there, so I have to add plus 5. Let me put parentheses around this. All of this is capital F of 8. And then I'm supposed to subtract capital F of 0. Well, what's capital F of 0? That's this function with x replaced with 0. So that would be 2/3 times 0 to the 3/2. And then I still have the plus 5. I'm just putting that in red so that we can kind of focus on that c value that I chose. Well, can you see already what's going to happen when I simplify this expression? Because I'm taking this expression right here and subtracting this whole thing, and it's in parentheses, I have to subtract all of f of 0. You notice that when I distribute this minus sign, I'm going to end up with a plus 5 and a minus 5. And that constant that I chose, that integration constant that I chose a value of 5 for, is actually going to drop out. Well, let's just double check that and make sure. So I get 2/3. I'm going to write this in root notation again. Square root of 8 to the 3rd power. And I have a plus 5. And when I distribute this minus sign, I'll have minus 2/3 square root of 0 to the 3rd. And now I'm going to have a minus 5. And what's going to happen to that plus 5 and that minus 5, those are going to drop out. And no matter what c value I chose, if I chose something like c equal to, I don't know, 17.4, it doesn't matter what value I choose for my c. In general, whatever c value I choose here, I'm going to be adding it when I figure out capital F evaluated at my B value, and I'll be subtracting that same C value when I do capital F evaluated at my A value. So I think you can see that whatever C value we choose, it's going to drop out anyways when I do my F of B minus my F of A. And so I would end up with exactly the same thing that I had at this point, 2/3 times 2 root 2, the whole thing cubed. All of this is minus 0. The integration constant has dropped out, and so I would end up with the same answer of 32 root 2 divided by 3 when I simplify that whole expression. So I get the same exact area. And it doesn't matter what constant we choose for C. And that's why we always choose C equal to 0, as we did up here in step 2, because it's just easier. Otherwise, you're just kind of have to write it and cross the C's out when you distribute the minus sign anyways. So when we are choosing an antiderivative, we might as well always choose the simplest one and choose C equal to 0 rather than C equal to some non-zero value. It's just easier. But it certainly wouldn't hurt if you want to choose C equal to 5 every time. You're not going to get the wrong answer. Okay, let's go ahead and